This is a first walkthrough of a deck prepared to lay out an approach to uncertainty for Physics B Lab. This will be a working draft, and you'll all see it. You'll have a chance to make input to it, and we'll add one piece to it and make some revisions to it between input from you and from the instructional team. So let's go. This time, let's really go. Okay. This is a slide you've seen before. It is from a deck, from this deck. This is a deck put together by Professor Mechtenberg, Professor Hildreth, and what we go on to do follows their approach. It covers the same material that they cover. It covers it a little bit more quickly, and it makes reference to this deck for a deeper dive. So you've seen this before, and there's a couple of key distinctions that are made in it that cut across one another. The first is between uncertainty that is due to the measurement process itself, and then there is handling uncertainty through everything that comes after a measurement in analysis. That's the first distinction in these very large sets of columns. And then, of course, there's further distinctions that are made inside each of those two areas between measurement and analysis. And then cutting across that is this distinction between random uncertainties and systematic uncertainties. And the idea here is that there are only so many of these areas. Why these areas in particular? Because the one thing we know empirically that experience in lab can do for you is broaden your sense of freedom of inquiry. And in order to push your mind into those various directions one could travel, there's a couple of experimental pathways that are laid out. One that begins with measurement, one that begins with calculation, one that begins with variation. That's the three areas that the analysis pathway is distinguished into. So there's a reason for looking in all of these buckets in particular that has to do with what labs can actually do for you. What I'm going to do is track pretty closely in the deck that comes right after this here. It will follow the same sets of distinctions. It will eventually touch on 8 of these areas, and in this particular first draft, just 7, and then we'll come back to the 8th one later. So in our overview then, following this large distinction in the columns, there will be 2 parts, uncertainty and error. Those are 2 words really for the same thing. They're used almost interchangeably. Sometimes one makes more sense in one context than another, but uncertainty and error taken as a whole in measurement first, and then beyond measurement in analysis. Managing uncertainty in measurement, and here you can see I've grabbed a couple of the numbers from that first slide. I'll stop doing that after this slide, but just to show that we're tracking. It takes us into 3 important areas, 3 important terms that are related to one another in an important way. The first is total error. That might be random, might be systematic. Total error is a measured result, and you measure it. This is measured uncertainty in measurement. The 2 measurements are there on purpose. It's a measured uncertainty in measurement, and it's determined by repeated measurement of the very same quantity. Now, what's that same quantity is up to you. We could, if you know a person comes into the room, then you know roughly how tall they are. You could guess 5'5", but it's not impossible that they're 4 feet, and it's not impossible that they're 7 feet. And so there is a standard deviation here away from this average height that one could take. And yet these are very different people, and yet we're treating them as the same for the purpose of the height of a human being. This is so always. So when we repeat measurement, it's obviously different in time. It's different in any physical processes that take place in time, but we abstract from all of those things. So we decide this is the same, and we take it over and over again, and then we report all of that as standard deviation. We'll look at how to do all that shortly. So the idea behind total error is that you've got to measure repeatedly and calculate it. Now, tool error is related always and only to a specific tool. It's a tool that you may have, maybe the best tool you have at your disposal. It may be a tool that was assigned to you. And there is some maximum limit of tool precision, which is really just the optimal standard deviation, as the people who manufacture the tool and investigate it and explore its capabilities in the best of circumstances, they come up with an error. Sometimes that's expressed as resolution. Sometimes it's expressed, it could be expressed as a plus and minus, a single standard deviation, or it could be expressed at a higher confidence level. All things we'll look at down the road. But the tool error comes from the manufacturer. So what do? You look it up. You may have to, if you can't find it through looking it up, you may have to reason from the number of significant figures, for example, that a device actually shows on a digital device. You know that it can't be any more precise. Your use of it, anyway, can't be any more precise than the last digit that it gives you. And then finally, we can pull out another piece called process error, and this is just all the things, all the dimensions of the total error that are not due to the tool error. This is an area that's worth pulling out, because it's the one area, given that you're using a tool which typically costs money, it's expensive to get, all you have in your hands is how you use it. The context you use it in, the techniques you use, etc., all those are bundled into process error. And we pull out process error from the total error by subtracting the tool error from the total error in quadrature according to this formula. And most of you have seen this before. How do you calculate the standard deviation? I'm not going to go through this. These days, it's a command in a spreadsheet most of the time. It's worth walking through this, but probably not worth your listening to me walk you through it. Do walk through it and notice just a couple of points on the slide at the bottom that I do want to draw your explicit attention to. You've got to express standard deviation in the right amount of significant figures. As a rule of thumb, you only are entitled to a single significant figure unless you've taken, say, 10,000 or so measurements repeatedly, in which case the process of measurement, repeated measurement itself, begins to entitle you to more significant figures than one. But the rule of thumb is, for you in this lab, just use one. So you should understand this. Arrival at a standard deviation, which is the same as the total error, as the fruit of repeated measurement. And it's the very foundation for all your other uncertainty management. You can only preserve the precision you have, and you get precision by taking repeated measurements of the very same thing. Once you have that total error, you can then calculate the process error from it, and I won't walk you through this detailed example also. I will only suggest that when you do it, double check. You can set up columns in spreadsheets to do this, but always check to make sure that it makes some sense. One more point about measurement error, and that is the idea of a normal distribution. So if you are dealing with things that are different because of simple random fluctuations in nature, you'll generally get a distribution of measurements of that very same quantity, which will fall randomly in what's called this normal distribution. And when it falls in this normal distribution, there is a percent of the total data that will fall within the range of your standard deviation. So one standard deviation will typically capture 68% of the data, 2 will capture 95, 3, 99.7, etc. Sometimes you have to go higher. All of this is explained in more detail if you chase this link here in the lower right. And if I forget to mention that these links are here, they are in several places. So dive a little deeper if you'd like to. So confidence levels, you'll hear talked about, and this is the context for them. So we talked about two parts for our review. The first one we've just finished, which is uncertainty, error, and management. Please notice here that everything about total error, tool error, process error, all of that gets reported in the experimental data section of your lab report. We're going to move on now to talk about uncertainty error beyond the management, the preservation of error, and all of that will go in the experimental analysis section of your lab reports. This is not a hard categorization to retain, but I can tell you that some of you are not yet retaining it. So this is an accounting deal. Please just internalize it and follow this rule about which parts of reporting on uncertainty go in which sections of your lab reports. So let's move on then to uncertainty error in analysis. Let's just recall that we're in this section of this approach to uncertainty that falls in this analysis section here, and it's broken into three parts in the work that Professors Mechtenberg and Hildreth have done, but I'm going to break it into four, just adding one small point in another section. And we'll walk through each of these four and then we'll be done. We'll go quickly. First, sometimes you simply multiply, for example, when you do unit changes, you're simply multiplying a given quantity that has an uncertainty associated with it by an exact number. You're used to doing this when you change units and preserve significant figures. You might remember that when you multiply quantities with significant figures, you preserve the least number of significant figures of the various multiplicands, but that exact quantities you should treat as having an infinite number of significant figures, and so it's always the other one that limits it. The same thing is going to be true. There's an example here underneath you can follow if you like, but the same thing is true to uncertainty. What's really happening here is that you're simply expressing the very same quantities, including the very same uncertainties, just differently named when you multiply through. That's the first point. Here's a second one. Oftentimes we move from an arithmetic to a geometric representation of data. A rule of thumb is that whenever it's helpful, you should do this. Always ask yourself whether a plot is useful. Even a bar chart can sometimes illuminate the relationship between data. So whenever you use a geometric representation, always indicate uncertainty spatially. And the rule of thumb is that an error bar is a single standard deviation, but you should always say that is so, or that you're using to 2 standard deviations and a 95% confidence level, etc. Always say that in the captions of any plot you create. Now, whenever it's possible, always, not just every chance you can, you should construct a mathematical model, and that's known as regression analysis. And if that mathematical model is a linear one, which it often is, it's very convenient to do a linear model, then the y equals mxb formula is familiar to you. Look here at error bars in one dimension at the bottom in the bar graphs in 2 dimensions when both variables have got uncertainty, and here you have these x and y error bars in the central plot, and now we're all the way up to the top plot in which we're actually fitting a function. We're doing regression analysis, that is, and there are error bars, of course, there. And then there is an r squared value, and that is technically known as the coefficient of determination, and it's one of a number you can use to capture goodness of fit. This is how uncertainty is expressed in a geometric expression. That is, whenever you're plotting. Finally, or almost finally, second to finally, we manage uncertainty sometimes through comparison. It could be that we're comparing a part to a whole. that's what relative error does for you. And then sometimes we're comparing a measured value to a standard, and that's what percent error does for you. And we capture uncertainty, we manage uncertainty when we compare through these two expressions, not complicated. But then the last point we'll make in some detail is that we manage uncertainty often through calculation that involves multiple variables, each one of which has its own uncertainty associated with it. And we call that management error propagation. The idea is that the uncertainty of the variables in a function have an impact on the uncertainty of that function the function's value as a whole. So if y equals x squared plus y squared, then how well we know x and how well we know y both have implications for the function. I think I used y twice there, but if y squared equals x squared plus c squared, the point is right that the uncertainty of each of those variables on the right has an implication for how well we know what we calculate from it on the left. Here's a general expression. This particular one has three variables, and it represents, and it's got some parts laid out to match some English below. When we propagate uncertainty through this equation, we find that uncertainty, the total error of y, say, the sigma y, by adding in quadrature all of a series of things. And every one of those things in the series, every one of those things that we sum up, is a product. And it's a product that makes some sense. It's how dependent is that function on that variable individually, multiplied by how well we know that variable individually. That makes some sense. You can follow the little green and red brackets if it helps you. And this is the formula that we'll follow when we do it. Let's look at some examples. We'll look at a couple. I'm not going to walk you through these examples because they're clearly laid out and you'd be better off doing it on your own. But here's example 1. This is a very simple two-variable case. And here, in the second example, is a couple of different ways to calculate the very same thing so that you can see the difference that your pathway might take. Which way you decide to calculate g, whether dropping a falling object or whether, say, using a pendulum at a very small angle. Both of those are ways that are often used, and they have different implications for error, and I'll let you walk through. The key thing here is to understand how the partial derivatives are taken, how this whole thing is set up. There are two video helps here for partial derivatives, and one of them, and you can find many of these, but I grabbed Sal Khan's presentation on how to take, in the sense of how to calculate partial derivatives, and you can follow that if you need some help. It's just like taking a normal derivative where you've got other parts in it that you just hold constant. That's the short of it. And then the question is, how do you visualize partial derivatives? And there's a physics videographer who's helped us see that, and I linked to his video here too. So here is the last thing we'll say. To summarize here, as a checklist for lab reports, you want to break these two into the two areas, remembering that uncertainty in measurement goes in your experimental data section, uncertainty beyond measurement and analysis goes in your experimental analysis section, and there's only so many points and basically three sorts of equations that you need to work with. I'll let you work through this, digest this summary, and we can assess together whether we can make it better. But for now, that's it. Thanks so much.